This is the beginning of chapter 5, and this is on chapter 5 is on work and energy. Work and energy. We'll talk about a lot of different kinds of energy, or there are many different kinds of energy, but in this chapter alone, we'll be talking about energy that's associated with motion, or energy that's associated with the potential for motion. So, for example, if I take a ball and I throw it, I'm giving it energy that's associated with motion because I'm causing it to move. Well, let's say that I take a object and I hold it up above the ground by some height. If I let go of that object, obviously it's going to fall. So by putting it into this position, I've given it the potential for motion. And a lot of objects have the potential for motion, and it's not just objects that are held to a certain height. We'll talk about different types of potential energy, we call it. That is the potential energy due to the gravitational field, and then also potential energy due to elastic objects like rubber bands, for example. All right. Now, collectively, these two types of energy, the energy associated with motion and the energy associated with the potential for motion, these are called mechanical energies because they're associated with motion. And this is in contrast to things like chemical energy, nuclear energy, and even thermal energy. So later in the semester, we'll talk about thermal energy in terms of how the objects are moving. So in a lot of ways, it is an energy that's associated with motion. But we'll get to those later in the semester. At least we'll get to the thermal. Now, work, which is very closely related to energy, and in fact, we'll get later to the work-energy theorem, which says that these two are basically the same, that when I do work on an object, I increase its energy. Yeah. So anyway, where was I? So we'll talk about the work-energy theorem, so that when you do work on an object, you increase its energy. But first of all, work is done when a force is applied over some distance. The force is applied over some distance. So, for example, when F and D are parallel, so if my force and my displacement are in the same direction as I have it here, I have then I can say that the work is equal to that force times that displacement. So here, for example, I have a force that's acting in this direction, and that force causes the object to move that distance. Then I can say that in this particular case, that work is equal to force times delta x. Now, the unit for work is the joule. And the joule, which is a person's name, is capitalized when you abbreviate it. It is equivalent to, and you should be able to break it down into its basic SI units. It is equivalent to 1 Newton meter. And of course, a Newton is not a basic SI unit. A Newton is a kilogram meter per second squared. And then I add a second meter. So these are the basic SI units of the joule. Sometimes you'll see work also as a Newton meter. So don't be thrown off. You can either see work written as a Newton meter or as a joule. I like to use the unit joule so that because later when we get into energy, we'll use that unit for energy as well. Now, if F and D, the force and the displacement, are not parallel, the component of the force that is in the same direction as D or parallel to D is the only component of the force that does work. So here I'm looking at my displacement is in this direction, but my force is in that direction. All right. So I'm looking at the component of the force that is parallel to the vector D. And of course, in that case, the component of the force that's parallel to D is going to look like this. It's going to be F cosine theta. All right. And it's going to be the product of these two values that will give us the work. So we can come up with a more general term for work. It's going to be FD cosine theta. and this is going to be sort of our working definition for work, that it's the force times the displacement times the cosine of the angle between them. And that cosine of the angle is simply to take the component of the force that's in the same direction as the displacement. Now up here, we didn't write this, but the angle between F and the displacement, the angle theta, was equal to 0 degrees. And so it was sort of implied here that we had cosine of 0 degrees, but of course cosine of 0 degrees is just equal to 1. So that expression just simplified to force times displacement. All right. So anyway, that's our working definition for work. Now, here's our x component of our F cosine theta. And so in this case, our work would be equal to force times delta x times cosine theta. Now, if there is no displacement in the direction of the force, there's no work done by the force. So consider you're carrying a bucket of water around like you tend to do, right? You're just carrying a bucket of water around and you're not exerting any net force on the bucket, right? So you're neither moving it up or down, you're not accelerating it in any direction, you're just moving it around at a constant velocity. In that case, you're doing no work at all, because you're exerting no net force on the object. All right, so dissipative forces such as friction also do work, but they generally do negative work. Now, what do you think? Do you think work is a scalar or vector quantity? You might not know right off, but work is a scalar quantity, so it has no direction. Right? The work has no direction at all. So this negative then means not that the work is in the negative direction, but that instead it's dissipative. So negative work will take energy away from an object. And this is, for at least friction, it's because the displacement and the force are at least often in opposite directions. And for our standard definition, our working definition for force, for work rather, FD cosine theta, you see that if we have an object that has a force in this direction, but a displacement in the opposite direction, then the angle between these two is 180 degrees. And the cosine of 180 degrees, of course, is -1. So anytime you have a force that's opposite the direction of the motion, that's going to give you a negative work. And again, that negative does not mean direction. That negative means that the work is dissipative. That means taking energy away from an object. All right, so let's look at this quick test. You know, I put the answers on here by accident, so let's just look at them. I actually don't have this on an online quiz, so, but let's just look at them. So which force of these does no work? And the answer is A. And the reason is that, well, first of all these blocks are moving to the left. Pardon me. Okay, so each of these blocks is moving to the left. They're all moving in this direction. So which force does no work? Well, in this case, I have a force that's acting up, and the displacement is to the left. And so the angle between those two is 90 degrees. And if I just go back to my definition, FD cosine theta, well, the cosine of 90 degrees, of course, is equal to 0. And so that work equals 0. So this one does 0 work. Which force does negative work? That's going to be the force that is opposing the direction of the motion, which obviously is C, because the displacement is to the left, but the force is to the right. So it's opposing the direction of the motion. The forces that do positive work are those forces that are in the direction of the motion, here I have this force is in the same direction as the displacement, and this force has a component, at least, that is in the direction of the displacement. So it's B and D. And then the force that does the most work is going to be B. Now, the reason it does more work than D is because only a component of this force is in the direction of the displacement. So here, I would have FD cosine of 0, which is just equal to FD. And here, I would have FD cosine of whatever the angle is. And cosine theta is always less than or equal to 1. Or in this case, if the angle is less than 90 degrees, it's going to be less than 1. All right, so D is or B rather, is the one that does the most work. All right, so when you lift an object, do you do positive or negative work? Well, let's say that I lift an object, I apply a force in this direction, and my displacement is also in this direction, so that's going to be positive work. Well, I also have another force that acts, and that is the gravitational force, or the weight. Now, it acts downward, but the displacement is up, so this force actually does negative work. And again, that's not a direction for the force, but that means that it's a dissipative force, that it's actually taking away from the energy of the object. We'll stop there and put this in a quiz.